Okay, it seems that we're live. Hi everyone, and welcome to the first of now a bi-weekly series of community calls. This one is going to be on dynamic proof of location. Basically, we recently released some updates. Ryan wrote an update post on our Discord. We're going to go through and extend on that. And talk about our plans moving forward for dynamic proof of location. Also featured in the call, except Ryan, will be Ilya. Ilya is our expert for translating complex technical concepts and should give you an overview that no matter your technical background, should give you an overview of dynamic proof of location and why we're using LoRa for it. During this call, we will, after this short intro, we will go through recent release notes. Then Ilya and Ryan will talk over recent developments on LoRa, and then Ryan will guide you through the anatomy of a zone blog post recently published on our Medium blog. And then we will go through previously collected questions that have been sent in via Google form. And then hopefully we have also some time for community questions gathered through the chat window here on YouTube. But without further ado, I'll give over to Ryan for the release notes.
Hi, everyone. Thanks for joining the first community call of 2019. The first item on our agenda is just to update on the latest release notes from the developers. So we released the Foam 1.0 version of the map, which that basically indicates that we have a stable API that is now available for people to use. And so I'm just going to quickly go over what that release entailed. So the first aspect of this release is a new feature of the map, which caches your salt when voting in the browser. So previously, when you were voting during a challenge, you had this unique cryptographic salt phrase, but it was quite a hassle to manually save that somewhere secure and then remember which one is which. So you had to like label it, document it. And it was when it comes time to reveal your vote, you would need to retrieve this salt key and insert it into the app. And so we know that that is a kind of cumbersome process and adds a lot of friction. So this new feature caches your salt phrase in your browser's cookies. So that means when you return to reveal your vote, you would automatically have your salt filled out. So you wouldn't need to remember it or store it in that way. However, we would advise that you would still back up your salt somewhere because depending on your browser settings, it either will not automatically store it in your cache settings, or if you clear all your cookies or clear history, for example, that may clear the cache of your salt. So we still advise that you do back it up somehow, but hopefully this will improve greatly the user experience of voting and will do more to optimize voting, but ultimately a future version of voting will no longer be based on partial lock, commit, reveal, and we can use a more streamlined voting technique. But as we know, partial lock, commit, reveal is kind of the most usable form of voting for blockchains in this context at the moment. Next is that there was an update to the reward pool card. So if you're looking at an active challenge, there's more data about the number of tokens that are actually part of the challenge, what the reward pool entails, and what the winner of the challenge would get. So these are kind of the most recent features added, and I'll go into what will be coming next after. But kind of the biggest aspect of this release is that we now have a stabilized version of the API, which means that anyone can basically more easily hook into the data that is being generated in the map. And we know that our partners at Blockalytics of Caleb has been using our API, but now you can access it in this interactive version, and the link is in the release notes. And by the way, these release notes have recently just been posted to our Discord. We're going to be working on updating our public repositories, and future release notes will be posted on GitHub. And we're now providing JavaScript libraries to use that you can query our API. So the API is now stable and released, and then coming hopefully next week will be the updated developer portal. The current one can be found at developer.foam.space, and this will give really easy access to REST API queries and ways to pull the data from the map. And the final part about this release note is an unseen change, but we have been working on upgrading our backend to PureScript language version 0.12. And Rackley, one of our developers, has also added a major component to the PureScript language itself that was approved. So these are kind of just the updates of our release notes. We're currently working on things like notification statuses, easier ways to be notified when you've been challenged, a DEX integration, so for example, 0x instant, so you can easily swap and obtain tokens in the interface, and further out from there, we'll be moving into leaderboards, stats, badges, and rewards. So this is the latest release notes. And from there, I just want to walk back and introduce everyone on the call. So I myself am Ryan, co-founder and CEO of Foam. We then have Arthur, our head of growth and community, if you want to say hello, Arthur. Ilya, who will be presenting next, who's one of our lead architect engineers. And then we also have Daryl, community manager, and Brian, a marketing assistant. So if you guys want to say hello. Hey.
Hello.
Hey.
Yeah. Okay, and so with that said, we're going to pass over to Ilya. And so basically in our last update on Discourse, we showed the current status of our radio research and our kind of breakthrough with the thesis we had that you would be able to use consumer level devices and obtain the level of accuracy, time precision needed. And so the results that we obtained gave us a 2.2 nanosecond precision, which in the lab, but that equates to about a 4-meter accuracy. And so we're going to go over what radios we use, what firmware it's running, how we validated it, and then move over to the software side and see the current state of the time sync protocol and its development and how it interacts with Tendermint. And so with that, I'll let Ilya begin.
Hey, so as Ryan mentioned, we have some nice hardware goodies to talk about. So I guess a good place to start would be to explain what these little guys are. And these are development boards for an STM32 microcontroller, which is a low-cost microcontroller for making little electronic devices. The neat thing about these boards is that they have a built-in LoRa radio on them. So you kind of just have this one board that you can pick up for about 30 bucks or so that lets you just play with LoRa. So what's even more special about these is these are actually running the very firmware that demonstrated that we can get 2.2 nanosecond timing accuracy. There's only one slight modification to them, which is this little wire here going into an oscillator, which is also about $1 worth of modification. And the really cool thing about this is for about 30 bucks, we've demonstrated that we can get 2.2 nanosecond precision of when data arrives over the air over LoRa radio, which kind of goes against a lot of the common criticisms of LoRa for geolocation, which is, oh, you can't get accurate timing data. Yes, we can. And I think I'm actually going to go into a screen share right now where we'll show you how we acquired that, the exact lab setup that was used, and a quick demo graph of how it all kind of comes together. So if I can figure out how screen sharing works. There we go. And, infinite zoom of browser windows. So what we have here is these are actually connected to my machine over USB. There's 2 of them. That's why the lights were all on. And I'm just going to connect to one of them. I'm going to do a quick reset for it. And what's going to happen is I'm going to press a button. It's going to tell the other radio to start sending over a stream of packets to the other device, which is currently logging to the console screen here. So what we do is I'm going to kick it off. And we've sent out a train of about 100 packets. Sometimes the timing info isn't accurate, isn't coming out all at once, but you can run it a few times and have it happen again. So we should get 100 entries here. There we go. And so what you would then do is, this is of course just kind of like a demonstration dump, but the number on the very right here, these guys, is the internal counter that's inside the chip that's actually tracking when each part of the packet arrives. So what one can do is one can actually just take this counter number here, plug it into what is currently a spreadsheet, but is very easily done in software. So what you do is you plug the timer right into this, and it actually calculates a linear regression. So you could see that there's not that much variance in the actual timestamps of these versus like when it's supposed to be sent out. And in doing so, we've effectively demonstrated that, yeah, you can get some crazy precise timing data using cheap, off-the-shelf LoRa hardware. So should we segue into the other aspect of it, which is the actual time sync protocol? So while we've been working on getting hardware working, demonstrating that it can actually be used, we've also been working on implementing the Byzantine fault-tolerant time synchronization protocol that underlies basically the foam dynamic proof of location protocol. So what we have here is a simulator, which I'm about to kick off, which simulates currently 5 nodes, i.e. zone anchors, in a zone running the time sync protocol. So currently they are about to start syncing, and there they go. Depending on system load and other things, you actually see like in one of these two. Am I still screen sharing? Oh, I stopped screen sharing. Sorry, let's try that again. There we go. My bad. So what we have here is actually the time sync protocol running. It's about to start sending, well, pretending to send time sync packets. What this is simulating is 5 zone anchors running the rough sync protocol, which gets zone anchors, which obviously start at slightly different times, and it tries to get them synchronized such that the LT is within an acceptable range. So from that point forward, you would run a finer grain time sync protocol, which actually gets them down to 1 clock tick equivalent. Now, the neat thing about this is the protocol is completely radio agnostic. So right now, even though it's kind of being run like in the vacuum of software, it can just as easily be ran over physical wires, i.e. Ethernet, or using a potato as a charge carrier. But the real cool thing, obviously, and this is how it's being used in DPOL, is you would actually run this over the air in conjunction with the timing extraction capabilities of the LoRa boards. So this was written in Go, mostly because Go routines kind of have this. Go's concurrency model has really nice parallels with how things like this are implemented in hardware or resource-constrained devices like microcontrollers. So it makes it really easy to just say, hey, this is the algorithm. There's no questions of like, are we adapting any small like aspects of it because we're not running on hardware or something else. No, more or less the code is one-to-one between what would actually run on a board. And next steps going from this are actually linking it to the radios, which is already well underway. It's just not quite demoable yet. And we're also working on what we call the GeoPickle, which is a bunch of Raspberry Pis all acting as individual nodes. And again, they can be using Ethernet, they could be using any sort of peer link system, but of course, ultimately it would be radio. And the GeoPickle is a rack mountable cluster of Raspberry Pis where if you were to say have 4 Pis per zone, i.e. 4 zone anchors, you could, in a really compact space, simulate 10 zones effectively. So that's kind of the update of what's going on over here. I think you were muted there, Ryan.
Sorry, guys. Just to recap, Ilya, so you're currently working on the time sync protocol simulations written in Go, and partially we're using Go as well because it's compatible with the Cosmos SDK. And that is what provides us then the Tendermint consensus engine. So what you're looking at is a simulation of the radio protocol, but it's being simulated on a computer. And that would eventually then talk to the consensus engine Tendermint, well, it is doing that, and stores it there. And what Ilya was trying to say is that that simulation is happening on one computer right now. So you have different threads of your CPU acting as different zone anchors. The next thing we're doing is building this box of Raspberry Pis so that each one acts as a zone anchor. And instead of them all being on one computer, they'll actually have more latency because they'll speak to each other over interconnected cables. And because this protocol is radio agnostic, and so you could run it, for example, over wired computers, once we optimize the firmware that we just demonstrated, which shows that we can get 2 nanosecond precision, once that firmware is upgraded to have more functionalities, you can essentially plug out the wires connecting these Raspberry Pis and have them instead be radios. And just to kind of give everyone a better visual understanding of that, I just want to show a very quick clip from the office where me and Ilya made a demo that didn't really go through, but that's kind of just giving you a sense of what we can publish this demo later, but a sense of what those radios are. So right now, they're speaking to each other and logging it on the computer. And so we will then be updating that firmware. Here's showing that we had to add a custom microcontroller unit to the hardware device. So that is the device you can just buy off the shelf. We've added a custom part, have a custom firmware. We can time sync to that level. Now the firmware needs to be updated. And in the interim, we are basically optimizing and developing the firmware of the radio so they can do more sophisticated things. But here, in the meantime, we can keep optimizing the time sync protocol, simulate it, be running it on other devices soon, and yeah, eventually get to a point where we can have a shared open repository and people can run those on their own devices.
Yeah, it's an excellent recap. Yeah, for sure.
Yeah, so that was just kind of a more visual explanation from the update we provided in the last update. And I'm going to now move on to unpacking the anatomy of a zone. So, those are protozone anchors and what they may look like or how they may act. But I'm now going to go over our recent blog post, kind of just highlighting high level what it means to be a zone and what that actually is. So on Medium, earlier this week, we published this new post. It's going to be the first in a new series going over the topics of dynamic proof of location. And here we just wanted to introduce, really what do we mean by a zone and zone anchor and unpack those concepts a bit. And what we wanted to try to address is, what is a zone? What does a well-formed zone look like? How can we even trust a zone? And why would anyone want to run one in the first place? And so zones mean areas of coverage that are providing proof of location services. And a zone is made up of a zone anchor. This is just kind of a concept illustration. But what zone anchors do is they literally anchor down a zone and they keep it there. And they commit with tokens to do so. So the name is kind of important. And those devices that we just showed could be an example of a zone anchor, but they could also come in many forms. Different regions might require different frequencies or have different regulations from the government of what radios you can use. And over time, radios may become better and be different. So LoRa is only about 3 years old. Thinking about 10 years out from now, would we maybe have more advanced radios? So you can think of zone anchors as any kind of radio. Right now, we're experimenting with the LoRa one because it's low power, cheap, and accessible. But what this device would be doing is it needs to at least have 4 things to be considered a zone anchor. And that would be a foam-compatible radio, a processor to run the software, a clock and controller. Ideally, this clock is an atomic clock, so you have the most precise time with no drift or jitter. And zone anchors need an internet connection. And that internet connection is how they run the Tendermint algorithm and can actually share a state machine about the logs. Now, it is possible that a zone anchor does not have internet, and it is just a small beacon, posted on a tree in a field. They would need to subscribe to a zone anchor that does have internet. In our technical paper, we called the ones with internet zone authorities. But for these initial stages and the first round of public testing, we can assume that all zone anchors will in fact have an internet connection. And what we want to then move on to is like, what are the zone anchors actually doing? We have this kind of visual of the time sync protocol running on a console, but this diagram actually breaks down what they actually would be sending over the air. And what's striking about this diagram is actually, you can see we're actually working on the order of size of bytes. So one message is maybe only 100 bytes. So the kind of data that we're dealing with is significantly smaller than most blockchain transactions and other protocols. So you can think of LivePure, which is transcoding gigabytes of data, videos, or Filecoin, which is trying to secure a distributed storage of terabytes and terabytes of data. Where here in this protocol, the messages are significantly on a smaller scale. And what's also most interesting is about 80% of the message is actually the private key of a cryptographic signature. So most of the payload of the timestamp is extremely small. And this means that it's much easier to store for a long period of time. And when we come to verifying that data from the verifiers, when they read these logs of messages, that data is very simple. So the kind of algorithms you run to check for fraud can be done very computationally cheap compared to, for example, proof of work mining. So it's just an interesting aspect of the protocol where, you know, there is some sort of elegant simplicity to it that the time data is so small. And just another interesting notion about if we're thinking about an anatomy of a zone and what makes it up. So from a physics point of view, it's essentially doing what GPS does, you know, synchronize clocks. And then from that, you can use different triangulation techniques by taking the time difference of arrival of the messages. But because GPS satellites are in perpetual motion and moving, their algorithms have to account for Einstein's theory of relativity, and both general relativity and special relativity. Because one, they're moving really fast, but two, they have a different gravitational situation. It's just an interesting note that on the contrary, you know, zone anchors are actually committing to being anchors and not moving and be stationary. And over time, as people use them, the positions of zones become known so that one, it's easy to detect if one has moved and therefore it's being fraud, or, you know, you can always rely on that. So just an interesting note that other time-based projects that rely on GPS have to account for relativity and we don't. But you know, time is essentially relative, and as we've seen in previous posts, there is no master clock of the world, and you know, GPS uses even a different system than UTC time. So in foam, you can just imagine that a zone, once it's established, essentially maintains a quorum over time and space in their location, and they are the authority of the time and space situation there. And not only that, they have a financial incentive to do so. And they've collateralized their position by entering a service level agreement, which means they've staked tokens and they promise to keep this quorum. And if they don't, or they're found out, they're going to lose their stake. So a zone can just be defined as a set of pairwise connections between at least 4 zone anchors. 4 is because you have one for X, Y, Z, and a fourth for variance in time. And this is the same if you're trying to localize yourself with the GPS signal. Sometimes it takes a few moments for your app to show you where you are. That's because it's looking for at least 4 signals to be able to figure out your position. And when we see a zone form, it actually is an observable event on the blockchain. So we have this parent blockchain, which you can think of as Ethereum. And for the zone to even become part of the protocol or emerge, it has to stake these tokens. So that means anyone paying attention to the protocol or seeing it will eventually have the record available that a zone has appeared and it's hit the criteria it's promised to. That means there's at least 4 zone anchors. They've staked the proper amount of tokens. They're now publishing their data logs. As we'll see further, that doesn't mean the zone can get rewards right away, but at least when it emerges, it's an observable event on the blockchain. Yeah, and so basically the primary purpose of a zone is to then issue presence claims to customers. So this is really what differentiates foam from GPS. While we're trying to address a lot of vulnerabilities and spoofing risks with GPS, the primary thing we're actually providing that is different from what a GPS could give you or a different system is the bidirectionality. So that once a zone exists and is broadcasting its time, people can then use that service to not just figure out where they are, but then speak back to the zone and generate a cryptographic proof of where they've been. We call that a presence claim. So zones will be rewarded simply for running the protocol in the form of mining rewards, but ultimately they're looking to have a revenue model where they can service customers, and that would be the primary incentive for running the zone over time. So that was kind of just an overview of zones, and most of that material was previously published. But the one kind of new topic is how do we actually verify a new zone? So, someone has to start the protocol. And most of the kind of above assumes that a zone is established, that it has its staking requirements, and there are things in place to keep it accountable. And so we have these kind of mechanisms like verifiers, slashing additions, and staking. But they could be basically running a simulation, like Ilya just demonstrated, where you are simulating zone anchors and simulating a timesync protocol and pretending to be there. So we have this kind of dilemma. How do we know if it really is there? And so one way is that when the protocol begins, there's going to need to be trust anchor zones. So these are essentially zones that through a secure ceremony, which is not fully defined and we will tackle in a different post, a trust anchor can form. And that one is basically publicly known. It is a public event. So their locations are known, their data logs are public, and they can be trusted essentially. And what that allows is then congruent zones to appear around it. So for example, we're here in the new lab in Brooklyn, New York. And if you imagine that was the first trust anchor, other zones that appeared around our location would be able to build off of that trust anchor and establish legitimate zones. And as more congruent zones appear that are further away from the trust anchor, they can get looped into the system just by being overlapping with existing verified zones. And that can just essentially kind of spread out and spread out and spread out. And once you have multiple zones, they can all cross-reference each other, and this trust anchor is no longer needed. So that's basically an exclusive way to bootstrap a new area, or one of the ways. But that doesn't exactly address the fact that there still may be zones that appear in brand new locations, and signaling may be one of the reasons why they do so. Someone says, hey, that's great, there are a lot of contiguous zones in Brooklyn, but we're over here in New Jersey, and I'm going to start establishing a zone. So then that begs that question, is how do we know that zone is there? And so a new kind of area thing to consider is that there will be these spread out zones. So there won't necessarily be continuous coverage of all the land, but there still will be a total foam area. So there'll be a total amount of land you can calculate that zones currently cover. And to be part of this total foam area and be eligible for your mining rewards and the fees from your location customers, you will need to have enough weight in the system. And there'll be a smart contract called the Total Foam Area Reward. We call it TFAR, working title, of course. And this is essentially the mining contract and the slashing contract. So this lives on the root chain. And that's essentially looking at, what is the total foam area this zone is covering? How much mining rewards does it get? And some of that weight it's going to be looking at is how long has it actually been there? So I'm a brand new zone. I'm not yet eligible for rewards, and I've been running it for some time. So that means all that time I'm trying to prove my legitimacy. I am running the protocol correctly, and I'm posting those messages to the blockchain. So part of my weight is how long have I actually been doing that work. Some of the other weight will come from how much tokens have I then bonded? How much tokens have I put into the service level agreement to show that I'm backing my actions with money? And another factor will be, am I operating in an area with a lot of signals? Because that will determine my mining reward as well. However, if you're a zone in a non-contiguous area, so you're completely in isolation, what you're going to need, the biggest weight that will get you to be recognized by the TFAR, is that you actually interact with a mobile verifier. So this is a new actor in the protocol, where previously we described verifiers that sit on computers and read the logs of the zones and check for fraud. A mobile verifier would actually need to physically go to a zone and purchase a presence claim to contribute to the weight of that zone. And the way that this is not simple attacked is because it's not going to be by the number of these mobile verifiers you can get to come to your zone, because of course, if you have a big gang of cheaters, you can all just keep pretending to be mobile verifiers. It's going to be a threshold of the number of tokens associated with those mobile verifiers that are attested to your zone. So that means a % of the total supply issued will need to be attested to that zone. And so there, that means it's much more difficult to collude because you actually need people to take that amount of tokens. So it doesn't matter how many people you have. And what's more interesting is that because these zones are not continuous in land coverage, once these mobile verifiers that have, I should back up, a mobile verifier needs to have gone through existing zones to have that role. So it's been in Brooklyn. And what's most interesting about it is different zones may not be connected in continuous land, but once they are added and recognized by the TFAR, what this mobile verifier does is essentially goes to that zone physically to retrieve the rewards, allow that zone to be recognized and get mining rewards. What it's also doing is bringing in that new zone topographically into the foam network. So there are now actually connections you could trace by this mobile verifier was in a trust anchor zone. It's now gone to this new location. It's validated that one. Enough mobile verifiers with enough weight have gone to that one. And even though that zone is in a different location, it's kind of topographically being brought into the network. So this is just kind of the high level anatomy of a zone. As we are working on updated technical white papers and working on the code, what that actually means in terms of thresholds of weight and et cetera, will have to be hard-coded and defined. Sorry for the pause. I'm just going to go now through the questions that were pre-submitted and then move on to if there were any other questions that came up during the call. So the first question we just received is, what is the value proposition of foam? That's a great question. The value proposition of foam is that we're trying to build a consensus-driven map and full-stack spatial tools for Web3 applications. So what that means is Web3 applications will not want to rely on Web 2.0 data because it has a lot of issues and pitfalls that necessarily can't be relied on for smart contracts. And there is no incentive to keep it upgraded or have ones that are open source and upgraded. So with the foam map that we've launched, the value proposition there is to have a new way to incentivize verification of this data and experiment with incentive models of registries of how to build up that data set. More broadly, as we move into dynamic proof allocation, the value proposition is to offer a Byzantine fault-tolerant time synchronization service that can be trusted and relied on as an alternative to GPS, and then also open a new marketplace for fraud-proof attestations about where you've been, proof of location, so that you can actually purchase a presence claim, keep it private. It won't be able to be sold or tracked in the way your location data is done now. And for the first time, you can have this cryptographic proof about where you've been. And that information can then be utilized in other Web3 applications. So, and further, we're providing developer tools and a full spatial stack for basically mapping applications on the blockchain. The first application that uses that stack is the foam map, but with our developer portal and API tools, we are trying to provide a value proposition of spatial tools so other applications can hook into and use it. The next question was, do individual signal providers get a fee when users enter their zone? So the signal is meant to be a weight to show where there is demand for zones. And the zone then, if it operates in an area with a high signal, will get higher mining rewards for that. So there's a weight. And like I said, going over the blog post, these parameters will need to be hard-coded, et cetera. But you can think of signaling as participating in a survey. So you're basically saying, hey, I want coverage here, and I'm going to participate by staking tokens there. And there will be kind of a small reward if you are correct. So let's say I signaled and now a zone has appeared. Essentially, you can think of it that I answered the survey correctly. So there will be this kind of payback to signalers for being correct if they are. But otherwise, it's kind of an indirect reward to the zones as a weight. The next question was, I thought signals were going to be open source. So signals are open source. All the contracts that you can interact with now have been audited. So we've published audits on our public GitHub research page. And then within the foam map, there's like a modal at the top, and you can click and get a list of all the contracts. So the registry contract, the voting contract, the signaling contract. If you click them, it brings you to Etherscan. You can read the code there, so it is open source. You can read the code in the audit, but we will be opening a dedicated repository to host the contracts so they're more easy to find. But they currently are open source, and you can read them on Etherscan. The next question is, does the US Coast Guard Authorization Act of 2018, which establishes an upgraded terrestrial backup timing system for GPS, negate the argument that GPS can be hacked? Well, no, it doesn't negate the argument GPS can be spoofed or hacked, because this would be an alternative system as well. So the governments and authorities have become more and more alarmed with the vulnerabilities of GPS and are looking to establish a backup system. But as it stands, the core value proposition of foam is the proof of location. So the fact that you can speak back to the system and generate a proof and buy a presence claim. So even if some alternative to GPS is launched that is terrestrial, if it's not bidirectional and doesn't offer that service, it doesn't really negate the need for proof of location, especially in Web3 applications. The next is, how do we see governments participating? Ultimately, governments could be amazing partners, especially on the city level, as there are a lot of smart city initiatives. And for example, in New York City, they're hosting like competitions and grants all the time for the subway system. And some people have proposed using time-synced IoT radios to try and track that, because they don't even know where the subways are in between different stations. So I think there are a lot of opportunities to partner with governments on a national as well as city level, especially if they see the value proposition of the service as a public good. They could also provide access to locations of where zone anchors could be installed. And in consideration of our plans, someone asks, on New Year's Eve 2019, what will be our greatest accomplishment? I would like to think that that will be having tested the zone anchors in the field, defined a reference material for the foam developer board, and have multiple test zones in different locations and have our community members being a part of that. So I'm going to move on now to technical questions. And that was, is foam working together with the graph protocol with their bulk query system speed the foam map? I'm going to have Ilya answer this question.
So we have seen Graph Protocol's connector to foam. We're very humbled that others are building on top of foam. However, we are not actually working together with them. As it stands now, our indexing system is actually very much optimized for the map, like for map related data. So while I wouldn't say necessarily that their bulk query system will speed up the foam map, there are definitely some really cool applications that can be built with it. And again, we're glad to see people building with it.
The next question is the foam map still being worked on for better speed and UX improvements? The answer is yes. As I spoke about in the beginning of this call, we have 2 new features to the map. One is a UX one, which adds more information to the challenge card. The other is upgrading the voting experience so that you can store your salt code in browser and not have to necessarily keep track of it. So those are the latest features and UX improvements to the foam map. But we still have team members ongoing working on features and improvements to the user experience. As I mentioned, the most upcoming one will be challenge-specific notifications, as well as the DEX integrations for 0x Instant. The next question is foam susceptible to a hard fork as it's open source? The answer is yes. As our code is open source, anyone can fork it and build their own token curated registry. Any open source blockchain project is susceptible to a hard fork, and we have seen some successful, some have failed. If you wanted to fork foam, you would also then need to build your own backend and front end for the foam maps, and that's a lot of infrastructure. Anyone is open to either build their own front end using the current foam smart contracts, or if they want to experiment or do whatever they would like with it, you can also fork the code and do your own thing. But just to reiterate, anyone could make their own foam map interface with different features than we provide. It's essentially a client to look at the blockchain. So the code is open source, the contracts are there. You could fork it, or you could also build a different interface for that code. Someone else asked, what's the delay in the hardware release? I just wanted to reiterate, through our plans of our token launch, token sale, and protocol launch, our emphasis was on delivering the deliverables around the foam map, which we delivered successfully, and are really proud of the work that was done in that. And we were very clear that there was no set date for a hardware release. We hope this call kind of clarifies the work that's being done and what we've proven in 2018 in terms of what's possible with those kinds of radios. But we're actively working on the software and the hardware, and we will share more concrete dates when we have them. The next question is on the dynamic proof of location. How easy is it to expand deployment to Europe in rural areas? It's as easy as in a city, or if not easier. You essentially just need access to locations. And it would probably work even better in a rural area because there's not skyscrapers or buildings that will interfere with your signals. So in that sense, a rural area is probably ideal for testing. Someone else asked, does dynamic proof of location count towards proof of use? No, the proof of use parameters are strictly defined around the functionalities that were launched in conjunction with the token sale. So that includes adding points as well as using the singling functionality. And someone else asked, what is our vision and plan about the tech promotion for the hardware? So once the firmware is optimized in a way that we can run the software on it, we then want to basically specify foam developer boards and find a means to get them in everyone's hands and integrate that into what our meetups and promotions be. So really kind of activating people on the ground, getting the interest there. We see in other projects such as the Things Network, which is an open community of LoRa users, as well as other consumer products like Gotenna, which is experimenting with Bitcoin technology, that there's tons of people who want to be a part of these kind of networks, which we are aware of. So we will definitely be working on the plans to get those into everyone's hands. The next question is, are there any meetups for foam? The answer is yes. We have our first of the year coming February 12th, which will be hosted here at the New Lab in Brooklyn, New York, with a formal announcement coming soon. And we'll have a lot to share about that event. And then we will have more events. Probably the next will be in, we'll have a few more in New York actually in the next 3 months. But we'll also have events happening in Berlin coming up soon and more cities to be announced. Now I'm going to move on to the questions that came in from the YouTube chat. So the first was regarding zone anchors. Are they required to be run by different entities, or is it safe for one entity to run all the zone anchors in a zone? So the answer is no, you don't have to be run by different entities. So one person could be running a zone themselves and providing all of the zone anchors for that zone. But as I tried to discuss in the blog post, it doesn't really matter if it's the same guy running the zone or not, but they're going to have to fit all this other criteria. So that's like the amount of tokens staked, the amount of time they've been running the protocol, and this different weight. And if they're not contiguous to other existing zones and they're just by themselves somewhere, it's one guy running 4 zones, there are other things they'll have to achieve to actually ever get rewards. Next is, are there teams working on hardware packages to fulfill a zone anchor requirement? So as I just said, we're currently working on optimizing the software to be able to run that software, and then we'll be moving on to a developer board specifications and ultimately a consumer-facing device, so one that has like a plastic shell and looks nice. We think it's a little bit premature to be designing a consumer-level device. We're focusing now on working on developer boards and then having those developer boards be optimized for the first rounds of testing. The next question is, how will movement on land affect the zone anchor? Are those significant enough movement? So this is a great question about like earthquakes and tectonic plate shifting, and probably one of the biggest challenges to designing this protocol, because you want to have these service level agreements where they say, hey, I'm going to be available 99.9% of the time, and if I'm not available, I'm going to lose all my tokens I staked, or some percent. The slashing conditions will vary. But for example, if an earthquake hits and all the zones in an area go out, the protocol is probably going to have to account for that. So maybe a zone won't be punished if every single zone around them went out as well at the same time. So those are going to be really important factors to keep in mind when picking the final parameters of that protocol. The next is, what represents the best revenue potential? The answer is quite simply running the zone itself, so that you can think of as almost like a business, that you're committing to offering a service to your local area. And with that, then there'll be a marketplace for you issuing presence claims. And those presence claims could be charged in foam token, but you can also, for example, issue presence claims for DAI. And the token is basically a discounted cash flow for what future revenue you could make out of that zone. Of course, if you're don't want to wait to dynamic proof of location, you can also work on or join other efforts in applications that hook into the foam map and charge fees or develop revenue in those ways. The next is, could there be a similar mechanism to the beacon chain but inverted? I'm not actually sure how to answer what that question means, so whoever asked that, if they could rephrase it. And the next is there a list of public projects testing DPOL? So as we tried to make clear in this call, we're kind of internally working on dynamic proof of location and optimizing the firmware, and in parallel working on the software. And so once we can make that those things public and specify the developer boards, we're confident that there'll be many people testing it. Yeah, if I understand your question, it would be similar to slashing conditions in Ethereum, that if you break your SLA, you're going to lose your tokens. But of course, there's going to be multiple parameters to that. So it could be, hey, you were caught with too many fraudulent presence claims in your log, but you were still running accurately. Maybe you were slashed a small percent. Or hey, you were like offline for like 45 minutes. Maybe you're slashed a small percent. Or hey, you've like pretended to move locations that have messed up the whole zone, you lose a lot of percent. So the slashing conditions will change. Yeah, like I just said for the last question, natural disasters will need to be taken into consideration when finalizing the parameters. So for example, maybe the TFAR contract is not slashing you if all the zones around you also went out, and it could be potentially inferred that there was a natural disaster. So there are a lot of unknown unknowns as well with this. So that's why our efforts are really working on getting a way to get this in other people's hands so it can be tested in many different kinds of scenarios and different kinds of regions and different kinds of environments, whether it's rural or city-based. Okay, so that's all the questions we had. I can wait a moment if anyone has any more, but otherwise, thank you everyone for joining. We'll post a recording of this call, as well as announce the next call and the FOAM event that's upcoming.
Also, one last note, if you want to follow next community calls, there was a calendar that you can, I don't know what you call it, follow for Google Calendar, and we will post the bi-weekly events there. So if you add it to your calendar, you will see them pop up for the future. I saw that a bunch of people already did that, which is great, but just a hint. And otherwise, thank you.
Yeah, thanks everyone.
Thank you, everyone. See you next time.
Bye.